Betty Sue, Eunice. Did you happen to catch that neato magic act at the county fair last weekend?
Well, gee, I reckon I did.
It was real swell. What was your favorite part?
I liked the part where the lady was able to lie down on the bed of nails and got off scot-free.
Yeah, she must have really thick skin or something. I mean, one nail would hurt a lot, but a whole bunch of nails, that would hurt a ton.
Actually, it would hurt less.
Because of magic?
That wasn't magic. That was physics. You see, kids, to understand how this works, we have to understand a physics concept called pressure. It's my personal favorite.
Pressure? What's that?
Pressure is the amount of force over a given area. The force always creates a right angle to the surface.
It sounds like force and pressure are the same thing.
They're not quite the same thing, but they're directly related. You see, as the force on an object increases, so does the pressure, because of a direct relationship. But as the surface area increases, the pressure decreases, because they're inversely related. Let's take a look.
Oh gosh, I'm still a bit confused. How the heck does this whole pressure thing have anything to do with the magic show and the lady with thick skin from last weekend?
Well, you see, Sally, a nail has surface area. A lot of nails have a lot of surface area. The greater surface area will come into contact with the lady's skin. And as we see, how are surface area and pressure related?
I know this one, they're inversely related.
That's right, Betty Sue. So a lot of nails are going to have a lot of surface area.
And only a little bit of pressure.
That's exactly right. So because there's so much surface area in the mix, each nail doesn't exert nearly as much pressure on the lady's body as one nail would, because the forces are spread out.
Force? What force?
Well, first of all, there's the force of gravity. That's the force of the earth acting on the lady. Then Newton's third law.
Oh, I know that for every action, there's an opposite and equal reaction.
It sure is. In this case, it means that for every force one thing exerts on another, that second thing exerts an equal and opposite force on the first. So there's another force, the nail on the lady. Those are the forces that we're spreading out over more surface area. So she doesn't get poked nearly as hard because there's so much less pressure on every part of her.
Well, that doesn't seem nearly as bad after all.
It sure doesn't, once you get the hang of it. The pressure thing is pretty simple. Would you kids like to see a pressure, force, surface area all in action together?
Sure thing!
Okay, who wants to be like the lady from last weekend and lie down on the bed of nails?
No thank you.
Okay, fine. I understand if you two don't believe me yet. Oh, hey, can I borrow your balloon?
What's the balloon for?
The balloon will act like a person. Now, what do you think will happen if it's pushed down on one nail?
Pop.
That's right. Exactly. May I have another? Now, what do you think will happen if we put this balloon on a lot of nails?
Pop?
No, not exactly. Putting the formula to use, greater surface area means less pressure on the balloon. Putting the formula to use, let's try calculating the amount of pressure put on this balloon with, say, 1 millimeter cubed of surface area, or about one nail. Using the same constant force of 0.605 kilograms, the weight of our book, we plug it into the formula that we derived earlier to see that the pressure on the balloon is 605 kilograms per meter cubed on the balloon. In comparison to the bed of nails, where we kept the force the same, but increased the surface area to 100 millimeters cubed, once we plug and chug, if you will, we get the total pressure to be 6.05 kilograms per meter cubed on the balloon, much less than when it was on the single nail. Hence, when the balloon is on the single nail, it pops, but when it's on a bed of nails, it stays in its current state. Now let's take a look at force, the other part of our pressure equation. I'd like to do what I call a hand-waving argument. Watch as I apply a small force to this balloon.
It did pop.
Yeah, you're hardly doing anything.
Exactly. Now, watch as I apply a much greater force to the balloon. Watch out! We see here that the greater the force, the more pressure put on the balloon, hence it popping.
Golly gee willikers, a direct relationship.
You got it, pal. That's what I like to call pressure. So if we put this all together, we see that pressure has a direct linear relationship with force and an inverse relationship with surface area.
Thanks for showing us how the magic really works.
Yeah, that was great. Catch you later.